Okay, on to number 11. So we just got through talking about number 10. So this is E11 now. And the reason I'm showing both of these problems here is because the equations look very, very similar, right? But they are importantly different in that this equation here, I've squared both sides. And that's going to change what our answer is going to be a little bit. So compare what we're about to do with what we just did moments ago with number 10. So here we go. So let's see here. Again, this is rotationally symmetric around the x-axis. Again, all what we need to do is to figure out what the equation looks like in one of the hinged half planes. X-axis. Again, let's choose some part of the xy plane, part where y is positive. So z is 0, y is greater than or equal to 0. At which point, again, square root of y squared plus z squared turns into y squared. So this equation, y squared plus z squared equals sine squared of x, turns into y squared equals sine squared of x, otherwise known as y equals absolute value of sine x. Gosh, I'm sorry. Absolute value of y equals absolute value of sine x. Does that make sense? Okay. So said differently, either y or negative y could equal to the absolute value of sine x. And if sine happens to be negative, okay. No problem. So this curve here, this is actually kind of two curves, and it looks like kind of like that.
Where sine's positive and negative.
Yeah, in fact, let me write this a little bit differently. This is fine, but I'm going to kind of cross that out. What you might find more appealing is that y is equal to plus or minus sine x. So in other words, there's two. If y squared is equal to sine squared x, then either y is equal to sine x or y is the negative of sine x, one or the other. And here, there's y equals sine x. It's sort of that part of it. And then y equals negative sine x is the sort of opposite part of it.
Then you can have negative y.
Yeah, well, as far as this equation here is concerned, yeah, y could be positive or negative. But that kind of doesn't matter because, again, we don't really care about what happens when y is negative. So all this stuff over here we cross off, right? But what's important is that since y could be negative sine x, when sine x is negative, you'd get positive y over there. So these little bumps where there had been gaps are now filled in. Does that make sense? So now it's more of like a string of beads or something. There aren't any gaps in between. So when you take that and rotate around, now again, the pictures are going to be bad here. But you're going to have, something like that rotated around, and then you're going to have something like that rotated around, and then that little thing there rotated around. And critically, these join up. Whereas in the previous example, they didn't join up because there was no little bit of curve here. And the reason there was no little bit of curve is because y had to equal sine x and be positive. So if sine x was negative, well, there's nothing there. Here, y doesn't have to equal to sine x. Y could be equal to plus sine x or minus sine x. So if sine is negative, okay, well then y is equal to the negative of that negative number, and it's positive. So cool. And you get these little extra bits of curve like that.
So we can't show that they join up in the rotation, but if we have it in the plane like that.
Yeah, it's going to be really hard to draw. Yeah, exactly. So you're right. I kind of tried to you got me dead to rights. I couldn't show that these spheres were touching, and so I showed that the bits of curves that were rotating were touching. And that's just a way to kind of communicate. And by the way, if you don't think of that, or if there's some what you know to be an important qualitative feature that you're not sure how to draw, you can just say, these are touching. And that's totally fine. Yeah. Okay, cool. All right, let me stop this recording.